Hi everyone, you are watching Unit 2 Video 4. This is going to be an introduction to compound inequalities. Compound inequalities involve the words and or, and this might be a review for some people if you talked about compound inequalities in your Algebra 1 in junior high. The first kind are or statements. Or statements involve taking the union of both inequalities, and the symbol for union is a U. And this symbol means I'm just going to take everything that's in it. Take everything that is in the inequality. So for x is less than 2 or x is greater than or equal to 5, I'm going to graph each one individually. X is less than negative 2, all numbers to the left of negative 2. X is greater than or equal to 5, all the numbers to the right of 5. And that's it for the union. I get to take everything. If I wanted to test certain values in here, so say I wanted to test x equals negative 3. Is negative 3 less than negative 2? Or negative 3 greater than or equal to 5? And the answer is yes, because one of them is true. And so that works. If I wanted to test another number, say x equals 0, is 0 less than negative 2? Or is 0 greater than or equal to 5? And the answer is no. 0 does not fit either inequality, and it is not in my shaded region. Okay. So if I take a look at the next one, x is greater than 3 or x is greater than 9. Again, I'm going to graph each one individually. So greater than 3, all numbers to the right of 3. Greater than 9, all numbers to the right of 9. And as it turns out, this one is going all the way in the same direction from 3 on. Let's pick a different color to show the tests. Okay. Oh, that's better. So let's test a number like x equals 5. And so is 5 greater than 3 or greater than 9? The answer is yes. It's greater than 3. It's part of my shaded region, so it is a solution. If I want to test another number, say let's test x equals 9. Is 9 greater than 3 or 9 greater than 9? And the answer is yes. 9 is greater than 3. It fits that solution, so 9 is one of my solutions. So on an or statement, it's a union. You take everything that's in the graph, and any test number has to be true in only one of the inequalities to be considered a solution. So now let's talk about and statements. And statements involve taking the intersection of values. Symbol for intersection is an upside down U. And this means I'm going to take only what they have in common. Only the values that they have in common. Some people call this the overlap. Okay. Now this first one here, negative 3 is less than or equal to x is less than or equal to 7, is an and statement. I call it a sandwich inequality because the x is sandwiched between two numbers. Okay, so this is describing all values that are between negative 3 and 7. And so we shade it in the middle of those two numbers. If I wanted to test some values, let's test x equals 0. Is 0 between -3 and 7? The answer is yes, and that's why we shade it in the middle. If I wanted to test, say, x equals 10, is 10 between -3 and 7? And the answer is no, and so 10 is not part of my shaded region. Okay, this next one is not written as a sandwich. It's talking about all numbers that are both greater than 5 and greater than 0. So again, if I think of my number line, I want numbers that are greater than 5 and greater than 0. When I think about what they have in common, here are the numbers that are greater than 5. If I were to do numbers greater than 0, that would also include all these numbers in between. But because an AND statement is an intersection, we only take the overlap. We do not want to take these numbers here in between 0 and 5. They are not part of the solution. So again, let's pick some numbers to test. If I were to test x equals 7, is 7 greater than 5 and is 7 greater than 0? The answer is yes. 7 is both greater than 5 and greater than 0. That means 7 is part of my solution. But if I test a number in the middle, say 3, is 3 greater than 5 and is 3 greater than 0? Well, 3 is greater than 0, but it is not greater than 5. So the answer is no. Even though it's true for one of them, an AND means it has to be true for both, only what they have in common. And so for that reason, I think ANDs can sometimes be a little trickier. So once you have that idea of AND and OR, we can talk about solving compound inequalities. And here's an AND and an OR to solve. Basically, solving a compound inequality is just like solving a regular inequality. You're just going to do 2 in 1 problem. So for this first one, if I go ahead and subtract 1, you get x is less than or equal to 8, and add the 2 to both sides, you get x greater than or equal to 5. So that's the solution. Question is now, can I graph this solution? And so if I put the numbers on my number line, I need to think, where are the numbers that are both less than 8, less than or equal to 8, and greater than or equal to 5? And it is only the numbers in the middle. If I go outside either direction, I'm going to end up with one of these being false. I can also express these as an interval using interval notation. And for this interval, I have a beginning and an end. So it begins at 5, it ends at 8. I include the 5, and I include the 8. So there's 3 representations here. There's the algebraic representation, there's the graph, and there is the interval notation. Let's see what this next one looks like. It's an OR statement, so I'm going to take the union. I'm going to take everything that's there. First part, let's subtract this 2x from both sides, and I get 4x minus 4 is less than 0. Add the 4 to both sides. I get 4x is less than 4. Divide by 4, and I get x is less than 1. Over on this side, I'm going to divide both sides by -3. And we have to remember, when we divide by a negative number, that inequality does need to flip. And so it becomes x is greater than or equal to 3. And so here is my algebraic solution. X's that are less than 1, or x's that are greater than 3. It is an OR statement, so I'm going to graph each one independently. There's my less than 1. There's my greater than or equal to 3. And that's my OR statement. Just take everything and put it all together. The interval notation. Now there are two of these. One of them is from -infinity to 1, open bracket, and it is the union with closed bracket on the 3 to include it, all the way to the right, infinity. So again, you have the algebra notation, you have a graphical representation, you have the interval notation. All three of them describe the same solution. Okay, let's take a look at two more solving ones. Again, I'm going to solve each one independently. 3x is greater than 7. Divide by -3, so I flip. And it's -7/3. On the other side, I get 5x less than or equal to 22 when I add 1. Divide by 5, and I get 22/5. That is an and in the middle. So there's my algebraic solution. Graphical representation. Graphical representation for an and means I need to find where they overlap, where both of them are true. So this is negative, let's see the decimal equivalent, that's negative, or the fraction equivalent, -2 1/3. This is 4.4, I think. So I need numbers that are both less than -2 1/3, -2 1/3, and less than 4.4. So that would be in both directions. Now the question is, where do they overlap? Well, if this inequality on the right kept going, it doesn't start overlapping until it hits that -7/3, or 7/3. That part of the solution is my overlap. This is where they are both true. And so my solution does not include that first part of the number line. In fact, it doesn't even include the 22/5. And so when you were to write this in interval notation, it would simply be -infinity to -7/3, not included. So the algebraic solution shows both of numbers. But when you do a graphical solution or the interval solution, and you have to give the overlap, you have to give where they are both true, you only end up with what it looks like only one part. Alright, one more OR statement here. Let's take each inequality individually. So I have -4x is greater than or equal to 8. Divide by a negative, so I flip the inequality. On the other side, if I subtract the 3, get negative 15. Divide, do not flip the inequality, I get negative 3. It is an OR, so there is my algebraic solution. An OR means I'm just going to take everything. And so my graphical representation starts with numbers from negative 2, less than or equal, and then at negative 3, less than or equal. So this OR statement, I just need to take everything that is shaded as an interval that's from negative infinity to negative 2. You take everything that is shaded, whether or not they overlap. Alright, so solving compound inequalities. You end up with 2 inequalities to solve and then have to decide. On an AND statement, you're going to look for some overlap. In other words, where they're both true. On an OR statement, you don't care where they overlap. You're just going to graph everything. And then once you have those graphs, then you can write the interval notation. Okay. Let's take a look at this OR statement. Get the pen, not the highlighter. Again, solve each one independently. Negative 2x is less than or equal to 6. Divide by a negative, so I flip the inequality. X is less than or equal to 3. Or, here if I add 7, that becomes negative 20, and x is greater than or equal to negative 5. So here is my algebraic solution. It's an OR. So that means I'm just going to take everything. I am going to graph everything, and everything I graph becomes my solution. So if I start with negative 3, and I graph everything that's less than or equal to negative 3, I end up with the left side of the graph. If I graph negative 5 and graph everything that's greater than it, I color everything to the right. Turns out I've graphed the entire number line. So this one is a case where my solution is all real numbers. There's my algebraic solution, my graphical solution. Interval solution is all real numbers, or negative infinity to infinity. Okay. I don't care where they overlap because it's an OR statement. I want to take everything that I end up graphing. And in this case, every single number is covered. So last page. Your assignment is to take a look at the entrance slip. The entrance slip focuses on recognizing the graphs of ANDs and OR statements, and we will do some more solving in class. Thanks for listening. Bring good questions to us, and we will talk to you later.